Assalamu alaikum. This is MD Rizamia. Today I'm going to design diffuse phase high-gain multiphase antenna in CST. Okay, so before starting design in CST, so I'm going to discuss about some antenna parameters. Okay, so I took decided that I designed a parabolic parabolic re- parabolic reflector and a feed horn antenna. This parabolic reflector work as a high gain, and this feed horn antenna work as a multiphase. And my requirement is then fulfill as a diffuse phase high gain multiphase antenna. Okay, so the electromagnetic waves are comes along this path and pins this parabolic reflector and reflect it parallelly. Okay, so the dimension of my parabolic reflector and horn antenna, I discuss it's later one by one when I need its parameter. Okay, so now open the SGF. It takes a few seconds until we wait. Okay. Okay. So open the new template file. Okay. So from here, click the microwaves and RF optical. Okay. And from here, click antenna because we are going to design antenna. So click next, and our workflow is waveguide, horn, etc. Okay. So click and press next. And I want to do my workflow in the time domains. Okay, it's recommended for time domain. Click time domain and press next. Okay, I do not sense anything from here. So my minimum frequency is 10 gigahertz and maximum is 15 gigahertz. Okay, so basically we know that X band is started from 8 to 12 gigahertz and KU band is started from 12 to 18 gigahertz and K band is started from 18 to 26 or something, 27 gigahertz. Okay, so whatever. Due to the limitation of my laptop hardwares and the CST Eastern version limitation, it doesn't work in the K bands. Okay, 18 to 26 gigahertz, the simulation doesn't run. But in this range, 8 to 12 X band and Ku band, it's run, but its output is not so accurate. Okay, but let's begin. What will happen next? Later it can be seen. Okay, so event select event and far field. Okay, so from here I want to see the brands from 12.5. Then click the next. Click finished. Okay, so it take a few seconds for ready it. Make it ready. Okay, it's almost ready for design. Okay, it's ready for design. So click view and go to the work plan and press the, basically I need to remove this portion. So click this work plan. Okay, from work plan. Now go to the modeling and click local WCS, which is a three-dimensional cursor. Okay, I call it the WCS. Okay, so click it and we get here. Okay, so first I want to design the parabolic reflector. Okay, so then go to the curves and click the analytical curve. Okay, so name it a parabola. Okay, name it parabola. Okay, parabola. Name it parabola. And before that, we're going to its dimension. So let's move. Okay, in 2D dimension, we know the parabolic equation is y is equal to x square. Okay, but in 3D dimension, the x, x, x-axis, y-axis, and the axis here represent u, v, w. It's the same things, but you can see that there is no value in the u-axis, means x-axis, but it has only value in y-axis and z-axis or w-axis. So u0 and v is equal to t and w is equal to at square. Using this equation here, okay. So the value is ut is equal to 0 and vt is equal to t and wt is equal to a multiplied t t square. Okay, so a t square and the radius parameter radius minimum 0 to radius capital R. Okay, capital R. So click preview and parameter taken 0.005. Okay, so okay, and the radius I already take data from many online sources. The radius of the parabolic reflector is this is radius and 81. Okay, so the 81 and all this value are in millimeter. Okay, so my design, yeah, you can see. Okay, so click Q, press the pan and move it. Okay, rotate it. Okay, again plan it. Okay, now go to the modeling again. Click the in points, and click here. Basically, we move the 3D cursor WCS from here to here. So for this, we click this portion, and this 3D cursor WCS is moved. Now it's time to uh, identify the center exactly. Okay, so for doing this, click the go to the transfer local coordinate system. Basically, it's in that the transfer curve are move along with the dv axis, means y axis. So if I click, this is a positive v axis and this is negative v axis. Okay, if I write minus r, capital R, then it's move from here to the center. Okay, I just do this for exact for getting exact center of the parabola. Okay, now I got the get the para center. Now it's time to design the circle. So click curves and press circle and press escape button. And the radius value is already known, that is capital R. And the other thing will still remain same. The center will 0, 0. Then curve. Okay. Now click preview. Press OK. Now you can see that it's almost come in the parabolic shape. Okay. So if I rotate it, you can now see that it's already come in shape. Okay. Now it's time to use given the materials. So before do that, so go to modeling again. Press the create shape from the curve. Select the sweep curve. From the sweep curve, select parabola. Press enter, and again press circle. Press enter. Okay. So rename it instead of solid, the reflector. Okay, reflector. And the materials of the reflector is PC, pure electric conductor. Click preview and press OK. So my parabolic dish is almost ready. Now now it's time to give its thickness, because many manufacturer company are concerned about its thickness. So go to the components and click the reflector, and again go to the shape tools, click the shells, solid or thickness sheet. And right now, this time is to maintain the outsider thickness. Okay, so outside and rename it capital RT. Okay, shift RT. Okay, thickness. I click preview, and the value is 2. Then choose any value, but I want to give it only 2. Okay, you can see that a thickness is noticeable. Okay, that's okay. So my parabolic reflector is ready now. Parabolic reflector is ready now. So move it. Now it's time to design feed horn antenna. Okay. So the feed horn antenna basically located in the focal point of the parabolic reflector, but has this few distance from the parabolic reflector to the feed horn antenna. So before so for doing that, we're going to the going to the modeling and trace the uh, transform local coordinate system. And in this case, it's noticeable that it's move along the z axis or double axis, whatever you can say. So now go to the slide. You can see that this is the parabolic reflector and this is a feed horn antenna, and the distance is capital F, and this is part is waveguide and this part is uh, aperture horn. Okay, aperture horn, aperture, and this diameter is LT and LF. If I added three three parameters, then we got the distance from the parabolic reflector to the feed horn antenna. Okay, so next go to the write dw is equal to capital F plus capital LF plus capital LG. Okay. So click preview. If the value of f is equal to 111.8, 111.8, 11.8, and the value of LF is equal to 36.14, 36.14, 36.14, 6.14, and the value of field is equal to 13.63, 13.63, 13.63. Okay, it's okay. So my three-dimensional WC is moved as from the parabolic reflector to its due distance. Okay, so it's time to design the waveguide. So doing that. So before doing that, I'm going to the slide again. So this is my feed horn antenna. Okay, this is a rectangular shape, and this is waveguide, and this is x-axis. WZ represent x-axis and AZ represent y-axis. And WZ started from minus WZ by 2 to ending point maximum range is WZ by 2. Similarly, the minimum y-axis direction AZ is equal to AZ is equal to minus AZ by 2 to AZ by 2. Okay, and thickness is and z-axis dimension is LZ. Okay. So now go to the design tools again. So go to this port and click escape button and name it waveguide. Okay, rename it waveguide. FE waveguide. Waveguide. And the minimum and this is in x-axis is equal to minus wg divided by 2 to wg divided by 2, and this is minus is g divided by 2 to, sorry, this is capital is to the is g divided by 2, and the w minimum is equal to minus lg minus lg minus shift lg, and the w max will 0, and the material is a PC. Students, and click preview. The value of WG is equal to 10.7. Yes, from here WG is 10.7 and H is equal to 5.4. Okay, W is equal to 10.7 and click OK, and H is equal to 5.4. Press OK. So my waveguide is ready, and now press OK. Waveguide is ready. So it's if I zoom it, you can see my waveguide. Okay, so zoom out. Now it's time to design feed horn. Sorry, now it's time to design the aperture horn. So this aperture horn is draw this area. Okay, in this portion, in this area. So I have to move this WCS dimension is here. So in this direction is positive W, and in this direction is negative W. Okay, so for doing that, going to again the transform local current system, and W is equal to minus LF minus, sorry, mouse setup, W minus LF, okay, sorry, minus LF minus LG. Okay, click click preview, and okay. So the three-dimension cursor is moved. Now time to design the aperture horn. So going to in the slide, this is basically my aperture horn, and this x in the x direction is WA, and our direction is AC represent. Okay, and this is my W direction, WT thickness. No need to set this. So name it parabolic aperture horn. Aperture 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 horn. Aperture horn. Aperture horn, and minimum is equal to minus WA divided by 2 to WA divided by 2. Similarly, ace minus ace A divided by 2 to ace A divided by 2. Ace A divided by 2, and the minimum will be 0, and the maximum is equal to MT. Okay, capital M into T. So the materials remain same. EC, pure electric conductor. W value is equal to 21.46, and AC value 15.68. 20.46, 20.46, and this value is 15.68. 15.68. Okay, press OK. The empty value is 0.5. You can select any value. I put here 0.5. So my aperture horn is ready now. Now it's time to add aperture, okay, in this between them, okay. So to do that, go to the view and click it. Now zoom in, okay. Go to the modeling, click peaks, and set the distortions. Then move distortions. Then click peak and extend distortion. Okay, we're done. Now it's time to click the logged buttons and name is aperture. Rename it aperture, okay? A GURE. Basically, this aperture is connect this waveguides and this aperture horn. Okay, and this material is to remain same PEC and click preview. Okay, this is my feed horn antenna is ready. This is a rectangular shape, basically. So click OK. So almost my horn is ready, but basically, you know that horn is a hollow shape, but it's not a hollow. Okay, so before I do that, I have to connect these three port, waveguide, aperture, and aperture horn. So for doing that, I'm going to select waveguides, go to the Boolean, then click add and press the aperture. Now first connect these two waveguide and aperture, okay, and press enter. That means my two parts are added. Now it's time to add this aperture horn and this two portion. Again, go to the Boolean, okay, and press add and press aperture horn, press enter. Okay, my three aperture horn, aperture and waveguide are connected internally. Okay, so it's ready. Now make it hollow. For make it hollow, so click peak, and this is the portion. Sorry, again need to zoom. Need it to zoom. Okay, click the peaks, the back side, excite it. Similarly for the front side. Okay, done. Now go into the shape tools. Click the shell solid or thickness. Okay. Now in this type in time, so we do the for inside. Okay. For inside, the thickness is empty. Okay. Capital M into T. Click preview and press OK. So my hollow type feed horn antenna is ready. So my design is ready. Now it's time to give it excitation and uh, run it. Okay, so simulation run times. So before do that, I make it zoom for excited and the zoom very large. Okay, so click the big points and excite it. Okay, done. My excitation is done also. Okay. So this is my design. This is my parabolic reflector, and this is my uh, feed horn antenna. This is a rectangle shape. Okay, it can be a conical shape, whatever you can choose. Okay, it's up to you. So my excitation is done, and now go to the simulation and click waveguide forward. Okay, it's 50 seconds. I do not sense any value from here. I just keep same this value, click preview, and OK. Click OK. So if I zoom it, you can see the excitation port on. Okay, the only one put, so excitation is done. Okay, so my design is done and my excitation also is done. So it's time to simulation. Okay, it's time to simulation. So before simulation, I fixed it in a center. Okay, it's time to simulation. So now going to the home and start simulation. Okay, the simulation is run. Okay, calculating. Actually, due to my laptop configuration, its RAM size, the simulation is taken very long time, almost 13 to 35 minutes. So that's why I post a video. After completing the simulation, then I'll again come in. Okay. So here I pause the video. So my simulation is done. So it's time to check the result. So going to the one, the result is S parameter. From S parameter, select S unknown. Okay. So it can be seen that the frequencies start to almost 65 decibel to here, and this is resonance frequency, and it's going on. Okay, but it's good if it's good if it start from 10 minus 10 decibel to or less than 10 decibel, but it happens because of the frequency range we uses is X and Q, right? uh, Actually the parabolic reflector and the feed horn antenna operates in high frequency range. In K band, basically it's 18 to 26 gigahertz. Okay, but we are given it uh, 10 to 15 gigahertz. The frequency is very small. Okay, that's why it happens. And I do not use this value of K band because the limitation of this student version of CST, and also my PC also my laptop hardware system. So that's why I used it. But uh, it's a happy news for me that my parabolic reflector is working, and parabolic reflector and feed hunt is working for X and Q band. But if I put high range frequency, then it gives the proper output, and its efficiency also be increased. Okay, so this is my S parameter, and if I set its far field cuts F22, so it's a 2D dimension. If I select it 3 dimension, that is represent this is my 3D Z theta phi. It's not cover all because its efficiency is not 100%. So frequency is 12.5 gigahertz, radiation 1.050, total limits is minus 29.68, and direction 8.0 dBi. Okay, so this is my far field. And now if I now on to one thing, that VWSR, the value of VWSR is equal to let's look the voltage standing versus wave ratio. Okay, frequency and voltage. This in this the 10, 10.5, 11, and this the value of the voltage is almost 1. But when these voltage are when the frequency are increased near at 15 is almost near at K band. Okay, so that the voltage is increased. That means my uh, my design is working only for K band. Okay, but due to the limitation of this software or my hardware of my laptop, so it doesn't operate in the K band. So I just use this band in X and Q band mixes. Okay, so this is the value. And if I say the uh, port signal, I give just a port 1, and this is my port signal. Okay, the time signal. So okay, this is my port signal. Okay, and in 2D 3D dimension, I just take the E field, electric fields. Wait few second, it takes this time. Okay, electric fields, the result. Okay, this is my electric field. Okay, electric fields. This is my electromagnetic fields. Okay, and again the magnetic field is like that. Okay, wait a second. Okay, this is represent the magnetic field. Okay, so this is my design and simulation. Uh, you can try if your laptop configuration is high, or your CST version is a paid version, then you can try the higher band K band. Then you can get the better output. Okay, better output, and efficiency also be increased. Okay, so my device is high gain multiphase device is high gain multiphase. The antenna is working, and that is the great news for me. Okay, so thank you everyone for watching this video, and give your valuable time. Okay, thank you.